All right. Okay, guys, we're getting started. So, let's talk about connections between multiplication and division. Guys, quiet, please. Thank you. Awesome. So some stuff that's should be pretty obvious, like obviously 12 divided by 3. Oh, looks like an R. Is 4. So 4 times 3 is 12, right? We know this. Or 13 divided by 5 is 2 with a remainder of 3. Or 2 plus 3/5. Or 2 3/5 is a mixed number. So I mean, yeah, if you did 2 times 5 plus 3, you get 13. So why am I spending time doing this? These are obvious things, right? Because the polynomials, when you divide them, are going to follow the same kind of pattern, right? So for didn't leave myself enough room, did I? That's okay. I'll do it up here. For example, if you have f of x over, say, g of x, then expect something like this: a quotient plus a remainder divided by g of x. I expect that. So what this means is that f of x, let me erase this stuff down here. So it means that f of x would be g of x times q of x plus r of x. So when we did like polynomial division the other day, like let me kind of go back over here. When we did this, right? If I were to multiply all this by x minus 4, and then kind of get rid of, or actually just multiply the whole thing by x minus 4. Just say that. What am I thinking? If I multiply this whole thing by x minus 4, so after I distribute it, what would I have? I would have x minus 4 times 5x squared minus 4, sorry, plus 14x plus 56, and then plus 232 because I have to distribute to the 232 over x minus 4. All that's going to equal 5x cubed minus 6x squared plus 8. All of it's going to equal that, right? Because that's what I'm doing. Because right now I know that all this equals that chunk. So if I multiply both sides by x minus 4, yeah, same thing, right? So coming down to this proof that we're going to, and this is the proof of the remainder theorem that we're going to talk about. So again, f of x, this is probably do want you guys filling out. F of x equals q of x times g of x plus r of x. This is when dividing by x minus a the remainder is a constant. So x minus a is g of x, by the way. We're calling that g of x, just so you know. Just like we saw in the example I just showed you in the filled out notes, the remainder is a constant is 232, right? So what this means, yeah, go ahead. General rule, yeah. So therefore, f of x will equal q of x, that your quotient, q of x stands for quotient, by the way, times x minus a plus r. Where again, that's a constant. This is when, so then when x equals a, we get the following. And these just go away. So what does f of a equal? The remainder. And that's the proof of the remainder theorem. So whenever you divide some functions, some wacky function, whatever, any finite function, I just want to say, the remainder you get is the same thing as f a. F a is the remainder. So this is the proof of the remainder theorem. Now, if the remainder is 0, then x minus a is a factor, right? Also, a comma 0 will be x-intercept of the graph of f. So if we go back to examples 7 and 8, let me just clear this for a moment. Hold on, UV. So I go back to this, right? See here. F of x equals this, f of 4 equals 232. The remainder was 232. That's the same thing as f of 4. For here, you assume that you're dividing by x minus a, right? So what's in place of a if I assume the bottom is x minus a? What a equals 3, negative 3. So f of negative 3, the top is f of x, f of negative 3 would be the remainder, which is 1. So therefore, f of negative 3 is 1. So this is called the remainder theorem, which I think you guys saw last. I don't know if you guys saw it last year, but so that's what's happening. So we're going to do synthetic division, but in this case, not to divide the polynomial, but to evaluate the function. So we're going to find, really what you're asked to do is find f of negative 3. Now, if you want, you can plug negative 3 straight up. You think so? I don't know. You want to erase? Okay, either plug in or, and it's called synthetic substitution, by the way. So if I do this, 3, 4, negative 18, and negative 3, I put negative 3 on the outside. I drop this down, multiply and add, multiply and add, multiply and add. And you should get 6, I think. Let me double check. What do you get, UV? See, I beat you. Okay, so yeah, I am. Well, you'll see it directly. That's going to be negative 81, right? Yes. And then that's going to be 36. And now you're at negative 45 plus 54, so you have 9 minus 36. Yeah. Be careless. No, be careless. So that's why this might be a little bit more streamlined, right? So anyway, that you could do that. Does that make sense what I just did? We're good? Yeah, okay. Okay, example 11. Let's take a look at that one. So show that 1/2 is a 0, and then find the other 0. So this is the beauty about synthetic division, is that we can actually break down the polynomial pretty nicely when you use synthetic division. So I'll put 1/2 on the outside, 2, negative 15, 27. You can do long division if you want, but I think synthetic division is cleaner. And by the way, we expect 0 because you told us an x-intercept, right? We expect 0. There's no remainder, right? If you divide this by 2x minus 1, which is 0 for which means 1/2 would be the 0 of it. Yeah, you're expecting 2x minus 1 to be a factor, right? So anyway, let's work it out. Let's drop it down. 2, 1, negative 14. There you go. So definitely that's a 0. Then you got this, right? Now, before I get too carried away, what can I do to factor this? What's the first thing I should do? Go ahead, Catherine. Yeah. Mm-hmm. So actually, before we get too carried away, let's pull the 2 out first, right? Let's pull 2 out first. That'd be a good idea. And that should be pretty easy factoring. Oh, geez. So that becomes what? X minus 5. And you still have the x minus 1/2 from before. And that's the answer. Well, actually, it's not the answer. That's just, it's factored. So those are your other zeros, 5 and 2. Now, the fact that I knew that this would be 2x, so that's good. But if things that synthetic division always assume the form x minus a, just that assumes x minus a. So I have to start with x minus half. If I want to put the 2 inside, I can pull the 2 out. If I want to put 2 inside of x minus half, go ahead, make it 2x minus 1. But you have to be very careful because this is the quotient I get after doing this. Because this is assuming that I factor x minus half, not 2x minus 1. This doesn't assume I factor 2x minus 1. It assumes I factor x minus half, x minus that number. Then when I'm done at this point, if I want to put a 2 back in any of these 3 factors, go for it. You can't. So does that make sense? How we broke it down and got the other zeros, right? We're good. Okay. Okay. Let's keep moving. All right. So some of you probably you guys seen before as well. It looks really weird, but this is a polynomial where the highest degree is n, and a sub n is the leading coefficient, and a sub n minus 1 is the next coefficient, and so forth, right? As you go to the descending order of your exponents. So this is something called rational zero test. Any possible rational zero will take on this form P over Q, where P represents, let me get it put as a text box. P represents all possible factors of the constant term, or A0. And Q represents all possible factors for the leading coefficient, or A sub n. Sorry, I can't do subscripts with the Zoom here. So when you do P over Q, that's going to represent all possible rational zeros. So just hypothetically speaking, what if I had like 4x to the 5th power plus 3x cubed plus 2x plus 6, right? What would be the possible remember, rational number is a ratio of 2 integers, right? We're all, Captain, go ahead. You have a question now? Okay. So what would be all the possible rational zeros for this? It would be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6, all over plus or minus 1, plus or minus 2, plus or minus 4. You don't have to write this down because we're going to do this later on. But if I were to actually work that out, I'd have to divide each of these 8. There's 8 numbers in numerator. Of course, 8. But each of these by 1, of course, itself. Divide all these by 2. The one that would be unique to be 3 halves. Divide all these by 4. Actually, also 1 half would be unique. Divide all these by 4. I think 1/4 and 3/4 would also be unique, if I'm not mistaken. So all the possible rational zeros, again, you don't have to write this down. Plus minus 1, plus minus 2, plus minus 3, plus minus 6, plus minus half, plus minus 3 halves, plus minus 1/4, plus or minus 3/4. Okay, those are all possible. So how many possible rational zeros is that altogether? Count it. 8. More. 16. Oh. So now back in the day, we used to actually ask our students to like by trial and error, like find let's like I won't give you any zeros to start with. So you'd have like, well, let's assume 1 works or negative 1 works, and you'd have to test it. Now this would be cruel and unusual punishment. I said possible. You did that last week. You did that possible. So you guys had how much time ago? But yeah, there's a possibility. Oh, she didn't know this. No, we just can't. Okay, sorry, I know you late.
Can I take a step back and can you explain to me how you like got those in the first place?
The numbers, yeah.
Yeah, like the plus or minuses.
Yeah, where do you?
1, 2, 3, and 6. 4 factors of 4. 1, 2, and 4.
I mean, yeah, we guess based on.
So you're just finding all common.
Yeah, so the P's are this, so this. All the possible P over Q ratios are over there.
Oh.
Those are all possible P. Yeah. Now,
Wait, also,
Go ahead.
like, so P is for only the constant at the end.
Yes,
So if
exactly.
it's zero, then there's,
Right, correct. Yeah, but
But then what you do is you factor out a variable and then you get a new constant. And you work with that. Exactly.
P was for all of the coefficients.
Yes, correct. So there's only one leading coefficient. I mean, yeah. Yeah, you go.
So why shouldn't it be like root of 6 and like this?
That's not rational. It's gotta be rational.
Has to be rational.
Has to be rational, yes.
Oh, PV coefficient.
Oh,
Highest
that's the
power.
rational.
What was that?
If we're confused of the highest power.
Yes, exactly. Yeah, we're only guys. This is assuming. Okay, this is assuming we have integer coefficients too. Yeah, assuming we have integer coefficients. Sorry, I should have said that. Right, exactly. Now, this is part one. Just that you know, just to kind of emphasize this. This is possible rational zeros, right? So there's a possibility that none of these 16 work, and that would be really cruel. I would not do that to you guys. Well, plus, I'm not gonna even ask you guys to guess and check. Like, I think it's just stupid, to be honest with you. I think what I would do is I would give you maybe a zero to work with. I say here's a rational zero. Or if you get a calculator, but then other zeros will not be rational, they'd be imaginary or irrational. But at least I'd give you something that you could work with and to break down the polynomial afterwards. But this would be all the possibilities. But there's a possibility none of these work. That could totally happen. So that could happen. Okay, let's keep going, guys. Let's make sure we wrap stuff in good time. All right. So for number 12, list all the possible rational zeros. Well, this is easy. I give you guys an easy one here. There you go. That's it, right? Plus minus 1. So let's try them out. Let's see what happens. Let's try one out. By the way, you got to put 0 as a placeholder for x squared. Now let's also try negative. Now I know one's not going to work because all the coefficients are positive or not 0. Sorry, non-negative. So I know it's not going to work, but we'll just do it anyway. 1, 1, 1, 1, 2, 2, 3. Yeah, it doesn't work. So no. 1, negative 1, negative 1, 1, 2, negative 2, negative 1. No. So none of them work, unfortunately. So there are no rational zeros.
So they're all the 9.
Well, technically, when you have a complex zero, its conjugate should also be a 0. And if you have an irrational, but this is kind of this does get a little funny. We're gonna use a calculator and work it out. Yeah, it does get a little strange, but let's look at the next one. Let's look at example 13.
Wait, so what are the books for that?
You know, let's do it actually.
No, there's
Log form on us.
No, think about it. It could just be a negative decimal. It could just be a negative decimal. It's one of the.
what do we?
So 2 of them are not real, guys, and one's gonna be irrational. So yeah. Yeah. Let's move on. Okay, example 13. So all the possible rational zeros here, your P's or Q's, plus minus 1, plus minus 2, plus minus 3, plus minus 6. Okay. Now, let's break down the polynomial. So there's a little bit of trial and error if you don't have a calculator, but if you're told you can use a calculator, so let's do it. Let's use a calculator then. We could cheat. So see here. X4 minus x raised to the 3 power plus x squared minus 3x plus 6. Wait, I made a mistake. Yep, there we go. Okay, so definitely it's crossing at 2, so let's go 2. Also it's crossing at -1, but It's up to you which one you want to go with. You can start with either one. So we'll start 2. 1, 2, 1, 2, 3, 6, 3, 6, 0. Okay. See why I'm getting this. Now, if you want to do synthetic division again, you can. You can, because we can do synthetic division with -1 now, right? Or you can do factor grouping if you want. Right? Factor grouping works. What can you factor out of the first group? You get x plus 1. And now then you factor out 3. So you get x squared plus 3 times x plus 1. And of course, we also have x minus 2 as the other factor. So the question was, find all the rational zeros. Well, yeah, it's obvious our zeros are going to be this. 2, -1. And if you want to say plus or minus I root 3. But since you only want rational zeros, then these are the only rational ones that we have. Because the other 2 are imaginary. So. And remember, when all the coefficients are real, if you have one imaginary zero, its conjugate is also going to be a 0. So that the imaginary zeros come in pairs. Because otherwise, you'd have an imaginary coefficient. Okay, we're okay? Good. Okay, last page. All right. Why don't you guys try this on your own? Tell me what you guys get. Just try it really quickly. I'll freeze the screen, and then we're done. Hey guys, let's work on it.
It's gotta be.
Guys are slow. Just kidding.
So the possible zeros are 1, -1, 3, -3. All you have, 3 has -3 halves. You just, you know, if you want to trial and error, go for it. But you can also play the top to get one of them. Once you get one that works, it's pretty smooth sailing after that, right? How do you have a question?
No.
So there's to it, pretty straightforward stuff. Solve just review, just make sure you know these are skills that you guys find zeros, functions.
So, any questions? It is, yeah. I have plus minus 3. Yeah, it's kind of hard to read from your angle, probably. Yeah, Andy, go ahead. So you just graph it and you find one of the x-intercepts. And then once you find one of the x-intercepts, use it for synthetic division. And then once you have the polynomial broken down, just do your algebra skills at that point, like factoring or whatnot, you know.
Your factors, is this x minus 1 or x plus 1?
X minus 1. If you see 1 as a 0, it's x minus 1. It's always x minus a. You skim that form x minus a. So when -3 works, x plus 3 is the factor, right? Not x minus 3, x plus 3. Yeah. Okay. So I think we're all set for today, guys. Homework. Guys, quiet down, please. Guys, quiet. Before we start the quiz, homework is this. So if you don't want homework over the weekend, because I do see you guys on Monday, because we have this funky schedule, right? Yes, 49ers tomorrow night, right? There's also Buffalo KC's a good one. Detroit, Tampa, Baltimore, Houston, But there should be some good games this weekend. So anyway, homework's right here. You guys are gonna be working on homework 4. I'll create a assignment schools so you guys know exactly what you have to do. I'm gonna stop this and stop